Today we'll cover. All right, so we'll cover 3 topics today. First, where we left, that was the implementation of decoder using De-Mux, demultiplexers. And the next will be the ALU, design of arithmetic and logic unit, ALU. And the next will be, if time permit, then we will cover the diode switching matrix. And these three topics are remaining in your combination circuit. Then we'll jump to the sequential circuit. Okay, so I have given a glimpse of how to convert. If you see the Boolean function or the output of decoder and multiplexer simultaneously, then you can say how you can convert a demultiplexer into a decoder, right? So decoder using demultiplexers. Okay, so first of all, you should see for the decoder. Let's suppose I have a 2 cross or 2:4 decoder, isn't it? Okay, so there will be 2 inputs and 4 outputs. Each of these outputs will be the min terms of the variable whatever you will apply at the input. So let's suppose these are x and y. So this will be x bar, y bar. This will be, okay, this will be, आपको भी नहीं दिख रहा है ना? Okay, so what is the status? Those who are at their home.
Sir, not visible.
Is it not visible or blur? Means clearly
Sir, not visible.
So blur.
Okay, so now it is okay. So this second output will be what? X bar y, and now third output will be x y bar, and last one will be x and y. Okay, and if you see the demultiplexer structure, so you should have one input, and according to the selection lines, output will be decided, or you can say according to the output, the selection lines will be decided. So let's suppose this is my S0 and S1, and they are connected to X and Y. So if I say these are the selection lines, so whatever you input you have at the input of this demultiplexer, this is 4x1 demultiplexer. According to this, the this input will be steered at the output. This will be directed to the output. Let's suppose this is 0, 0. So then for this y0 output, you will have I. So how do you write a Boolean function for this y0? So I can write it like this: x bar, y bar, and I. Here for y1, x bar by I, y2, x, y bar, I, and for y3, these are my y3, x and y and I. Okay, it is clear. Now I want to realize or implement this decoder using a multiplexer. So you can see I should be 1, and this input should be connected to the selection lines. That's it. Okay, so when I say, when I will be 1 and x is connected to S1 and y is connected to S0, the 1x4 De-Mux will be 2x4 decoder with x and y variable. Okay, so this way you can implement 3x8 decoder using 1x8 demultiplexer. Now I want what? 3x8 decoder using 1x8 De-Mux or demultiplexer. So what you will do? There is nothing there is no rocket science in designing or realizing 3x8 decoder using 1x8 demultiplexer. You have one input, and this should be connected to 5 volt. And you have 8 output lines. Okay, so 3 selection lines will be your variable x, y, and z. According to this input, that is 1, this will be reflected to the output. Okay, so before moving to ALU, there is another combinational circuit that is known as comparator, which compares bits. Okay, comparator which compares bits. So let's suppose I have a comparator here which will have 2 input A and B. So there will be 3 outputs. What will be the 3 outputs? There will be case where A is greater than B. There may be one case where A is equal to B. Or there may be a case where A is less than B. So this is 1-bit comparator. Sometimes few questions comes from this comparator. That's why I choose this to taught here. But this is not in your syllabus. Okay, so what happened? There is nothing difficult. Means you write just A and B, and there will be 3 outputs. So 3 outputs: A greater than B, A less than B, and A equal to B. So when you say there will be 4 combination, for 2 bits there will be 4 combination. You will compare both. 0 is what? Equal to 0. Here A is equal to B. So this will be high and this will be 0, 0. So you will get high at this A equal to B. When you compare this, A is A to B. So here we can see A is less than B. So A is less than B. This output will be high and this will be 0 and 0. For the third case, A is greater, the remaining will be 0, 0. For this case, again, you will have 1 here and this will be 0 and 0. So now you need to write one truth table for each of this output, and according to this truth table, you will design the circuitry inside this comparator. Okay, so yes. Correct. Okay, so it is very easy. How can you write for this? This will be A B bar. This will be what? A bar B, and this will be your, yes, you need one XNOR gate. Whatever it is, you can find out with the 2 cell or 4 cell or 2 variable K-map. So this will be 1 and this will be 1. 0, 0 and 1, 1. You can solve it and realize this. This is 1-bit comparator, but you may see 2-bit comparator. There will be a comparator. So A and B are 2 bits. They are a stream of 2 bits. So you will have, now you will decide is A is greater than B, A is equal to B, or A less than B. So how do you write 2-bit comparator here? So there will be A0, A1 and B0, B1. Now because this is 2-bit stream, okay, A is 2-bit stream, B is also 2-bit stream. So here we will have 16 combinations total, and we will compare all this with this. Again, let's suppose here it is 1 1 and 1 0. So we'll compare this 1 1 with this 1 0. So this 1 1 holds the weightage of 3 and this is 2. So A will be greater than 2. Accordingly, you will write or fulfill the truth table for these three outputs. Okay. In this way, you can design 2-bit comparator. In comparator, there are 2 inputs. So each input may have 1 or more than 1 bits. However, there will be definitely 3 outputs. One is greater than other one. Second one will be equal, and then the third one will be less than. Okay. So this way we have completed the decoder using De-Mux and the comparator. Now we'll see the ALU. What is ALU? Arithmetic and logic unit. So all the computers in the modern day, or you can say the CPU, uses ALU. ALU is a combinational circuit which actually performs the arithmetic operation along with the logical operations, as the name suggests, arithmetic and logic unit. From the next time whenever they come, the housekeeping वाले, तो इसको भी आप थोड़ा सा बोल दिया करो कि इसको साफ कर दें. Arithmetic and logic unit. So abbreviation for this is ALU. In this ALU is a combinational circuit which performs basically 2 types of operation. First is arithmetic operations. Second is logical operations. What will be the arithmetic operations? Summation, subtraction, division, and multiplication. The logical operations will be ORing, AND, NAND, this type of operation. So this ALU is performing 2 operations. It means this ALU will be having 2 type of units. One unit will comprise of arithmetic unit and the second will be the logic unit that will perform the logical operation. In the computer, there will be a ALU which performs this operation, but there is a controlling unit also, that this controlling unit sends the information to ALU which type of operation you should perform. Okay, and from where it will get the bits or the information, so there will be a memory. So this is controlling unit, this is arithmetic logic unit, and there will be a memory unit. So we are interested in this unit only for the ALU. What is this ALU? We will design this. We will see how it works. Okay. So the general notation for this is like this. You find in the books, the ALU, they represent in this form. Actually, it is not clear. This is your ALU. So there will be input data A and B, and there will be one output Y. This is also a bunch of outputs. And which operation should perform, arithmetic or logical? There should be few control units, and these are called opcodes. Opcode, it means operation code. Okay, so if you are smart, then you can answer me which type of combinational logic circuit we should use for this selection lines? Multiplexer, exactly. Because there will be arithmetic operation and logical operation. So at the end of this unit, there should be one multiplexer which selects these two operations based on the operation code. Okay, for arithmetic logic, there should be one adder circuit. Okay, so you saw, I think the adder can perform addition, subtraction, multiplication also. Okay, so this unit, this ALU will comprises two combinational circuits that are full adder, or we can say parallel adder, and one multiplexer, or more than one multiplexer. So we'll see this. Okay, let's suppose I want at the output whatever we have provided this input plus 1. It is not logic 1. Here this plus means plus. Means if my input data is this, I want summation of 1. Otherwise, if you are performing a logic, the whole output of this will be 1. Logical operation, variable plus 1 will be what? 1 in the logical operation. It means here you are ORing A and 1. So we don't want it. I want this A plus 1. How my parallel adder or full adder will perform this? So this is my full adder. It will have A, B, and carry in, and C out, and one output. Correct? So you have A, B, and C in, and carry out, and output. Now I want at this output, which is why I want the data at the output should be A plus 1. What you will do? You need to connect B as a 1 and C in will be 0. This will be the one case. The second case can be B will be 0 and C in will be 1. Can be 1. If you put B equal to 1 at the input or C equal to 1 at this position, not simultaneously, then you can get this A plus 1. Now I want A plus B at the output. This is my second case, a second desired question. What I can do? There is no problem. You feed this A data here, B data here, and C in equal to 0. So the output will be your A plus B. And according to this information, whatever it is, C out may be 1 or 0. C out may be 1 and 0. For the third case, when I want A minus B, yes, you need one complement here. So you can put A plus B complement plus 1. So you require B complement, okay, and 1. So you can fit C in equal to 1 here, and B can be converted as B complement with the help of NOT gates. However, for this, in ALU, you need multiplexers to select which should I get. Means what I get, what I want, means B bar I want or the simple B I want. So you need one multiplexer to select complement of the data or the simple data. In the same way, you can obtain the multiplication and the division. Okay. So now we will design 1-bit ALU, and then we'll see how can I convert or how can I design the higher order bit arithmetic logic unit. Okay. I need to perform this addition here. I want this my arithmetic logic unit perform addition, subtraction. Third one is AND operation. The fourth is XOR. Let's suppose these 4 operations I want from my ALU. So you, first of all, for the subtraction and the addition, you need one full adder. Oops. This is my full adder. So there will be a carry in, and there will be a data A and B. A and B. So there will be a carry out, C out, and you will have your output here. This will perform your job of the addition and subtraction according to whatever the condition I have given here. If you want subtraction, then you can complement it and you can feed C in equal to 1, then it will perform means this addition. Okay. The next is AND operation. So now I need this for the AND operation. I need what? One AND gate here. So now A, and this is my B. So this will result, the output of this AND gate will result AND operation between A and B. I need OR also. Here I want OR operation also. So I can have one OR gate. So the output of this will perform the OR operation. And I need XOR gate for XOR operation. So here I have one XOR gate which will perform the XOR operation. And these are connected here. So overall, okay, we'll draw it later. Now see, to select any one of these outputs, what you need? Multiplexer. Okay, because this is my ALU, but I don't want at one time all this operation. At particular time instant, I want only one operation. Let's suppose I want XOR operation. So I will feed the data accordingly at this opcode. And I will say perform this operation. So you need one multiplexer. Which type of multiplexer you need here for the 4 inputs? 4 cross 1 multiplexer. So this is your selection lines S1 and S0, and this will be called as operation code. So when I say operation code 1, not 1, this will be 1 and this will be 2, this is 3 and 4. Okay. So will this perform your job of this four arithmetic and logical operations? Okay, when I say here 0, 0, it means it will perform the ending of this two. When I say 0, 1, this will ORing, and there's addition and subtraction, and this XOR. What happened when I want NAND gate also? NANDing operation or NOR operation between these two. So I may require one NAND gate here, and I will connect the input of this A and B, and the output will be connected to the multiplexer. However, I need 8x1 multiplexer instead of 4x1 multiplexer. Or one thing I can do, what is the NAND operation? Is it means NAND of the A NAND B is equal to A complement plus B complement. So for this case, if I want to use only one OR gate, if I connect two complemented signal here with the OR gate, then I don't need another NAND gate here. Okay. So for this, what I can do, I can choose one multiplexer here. I can connect one multiplexer to A. This will be my one multiplexer. And for B, you have another multiplexer. And this will be your selection line for this multiplexer. And it is 2x1 multiplexer where you have your signal A and your signal B with the NOT gate. and this selection line I will call this as a inverter, and this will be B invert. Okay, so I have one bus or one line here for A inverter, and I have another line here. I should use colored chalk, but there are no colored chalk in this box or class, so I have to write with this V inverter. So whenever this is 2 cross 1 and this is I0 and I1. Okay, so whenever I say invert A, it means there will be high invert. This is inverter signal, so I will put 1. So for 1, this multiplexer will choose A invert. So the output of this multiplexer will be A bar, and according to this will go. Okay, here also for this B invert, this will go. So this is the 1-bit ALU, which is performing here. Now it is performing 6 operations. I can also perform NAND and NOR. This was your NAND operation, but also you can say NOR operation using one AND gate with the inverted inputs. Correct? So this operation, this one unit is performing. Now what I want to design 8-bit ALU. So what I will do, I will take whole this as one block. There is 2 hodgepodge, but no problem. This is my 1-bit ALU, so I will connect it in cascaded order. Not cascaded, in such a manner that there should be 8 outputs. Okay, now 8-bit ALU. You should have this 1-bit ALU where you are having 2 inputs A and B. Similarly, the second one, and this will have your A0, B0, A1, B1. This is 1-bit ALU. And the carry out of this, you have carry out here. The carry out of this will be connected to the carry in of the next one. And here you have this. These are the 3 control. These are the 3 inputs for this 1-bit unit here, and these are the outputs you have. So each and every control bit or control line will be connected to this. Let me connect this. This is A invert, and another one you have B invert, and that will be connected. And this is C in. So C out of the first ALU will be connected to C in of the second ALU. This is your C out, and here you have Y0, Y1, and a similar way you have 8th 1-bit ALU, and this will be connected here. This is A invert, B invert, and C in. So C in of this will be the output of the previous one, C out of the previous one. Here you have C out. Okay, and this will be your A7 and B7. So in this way, this 8-bit ALU will be implemented using 1-bit ALU. Okay. So the final job of the ALU is what? To perform arithmetic operation and the logical operation. And it is a combinational circuit which is comprises full adder and the multiplexers. Okay, so mhm. No, yes, you can do that also, but you need to larger up this box, because here I have decided that this box is up to this line. It means these are three control units which I keep outside of this ALU. So for this particular purpose, I need to connect for each and every ALU. Okay. Hmm. Excuse me.
Sir, you are not audible.
Yes. No, no, it will be compulsory when, because now you are performing the operation with 8 bits. So there will be definitely 8 bits. And each and every time you want some operation from bitwise operation. Means you want OR of 8 bits and 8 bits. So what you will do? You will perform bitwise operation for each and every bits. So there should be, means each and this all these 8 ALUs will be working for each operation. You cannot means put one ALU in the hold mode, because let's suppose you want addition of 8 bits. So there will be 8 bit A and 8 bit of B, two variables. So addition, you cannot put this middle bits on hold. I don't want add this and this. I want only this 3 and this 2 bits. This will not work. Did you get it? No. लेट सपोज आपके पास ये है 4 बिट का ही ऑपरेशन है, लेट सपोज, एंड यू वांट एनी वन ऑफ देम, चूज एनी वन ऑफ देम, चूज एडिशन करना है. सो यू कैन नॉट से दिस इज नॉट A0, this is what A1, this is what A2 and A3, and here I define B1, sorry, B0, B1, B2 and B3, and each of this A0 and A1 will be associated to the first ALU. Now the second ALU. Similarly, the 4 ALUs. So if you want addition, it means you cannot accept this, the combination of A2 and B2. You need to perform addition of all these bits. Then only you can obtain the results of 4 plus 4, means 4 bits addition. Instead of addition, if you want OR operation for this 4 bit, सो आपको सभी 4 बिट्स का और ऑपरेशन करना ही पड़ेगा, देयर इज नो चॉइस. एनी ऑपरेशन यू कैन चूज. सो आपको सभी के लिए, सभी बिट्स के लिए पर्टिकुलरली बिट वाइज ऑपरेशन करना ही पड़ेगा. दैट्स व्हाई these are the control bits.
एडिशन में तो चलिए क्योंकि कैरी आउट आ रहा होगा जो मुझे अगले के लिए इन में लेना पड़ेगा, पर और के लिए तो नहीं, हर एक को चलाना.
So the carry will be 0. और के लिए यहाँ पे that's why first I dictated this 1 bit ALU. Carry will be 0 here, this will be 0, this will be 0. When you put just A0, B0, this will give and select opcode equal to what? Opcode equal to this. Let's suppose this is my 1. Opcode is 1, which will perform OR operation of 1 bit. So the output you will get A or B.
उसमें तो मेरे को सी आउट की जरूरत ही नहीं है, तो मैं
But sometime you will need C out or C in. That's why we should have it. It doesn't mean that you don't need at a particular time, so you can discard that signal for the complete. It is not like that. For some time or for other operation, you need that signal. That's why we have to keep that signal. If you don't want to operate that C in, so put C in equal to 0. This will not harm your operation. Okay. For addition, it will be needed, but he want that if I am performing OR operation, so I don't need C in. So put C in equal to 0. Obviously, मल्टीप्लेक्सर चूज करेगा वहां से, so वो ऑपरेशन चेंज हो जाएगा. Okay, so discuss this later. I think it is very easy. Just you got some misconception here. Otherwise, it is very easy. Okay, so now we'll shift to the last topic of today's lecture, that is diode switching matrix. Okay, so I'm writing two statements and tell me which combinational circuit they should hold. Okay, so first statement is a signal at input at one of the input excites several output. And the second is a definite combination of input of signals at input excites just single output. These are the two statements, and each of these are related to the combinational circuit whatever we have studied. So we have studied 4 combinational circuits that are decoder, encoder, demultiplexer, and multiplexer. So tell me, first statement satisfy which one? Read it carefully. If I say this is for encoder, is it true? Why? Encoder you have 2 or what is the structure of encoder? No. Yes, 2 cross 1 obviously, or 4 cross 2. 4:2 encoder. So now tell me, is it satisfying the encoder operation? A signal at one of the input excites several outputs. So now you have here 1 0 0 0. So what will be the output here? 0 0. Exactly. It means a signal at one of the input excites several outputs. This one is for what? Which combinational circuit? The answer is decoder. Isn't it? Decoder, how many inputs you have? N inputs and 2 raised to power n outputs. So a definite combination of signals at the input, let's suppose this is 0 and 1. So particular single output, this is not signal, this is single, isn't it? Yes. Single output will be high. Okay. What if I want n number of inputs excite m number of outputs? It means I will give a definite combination of inputs at the n input, and I want as a result that m output should be high, or m output should work. Here it comes the picture of what? Diode switching matrix. So this is the use of diode switching matrix. What is the spelling of diode? This is diode switching matrix. Here you will have diode as a switch. Okay. And what is the application of diode switching matrix? So this is used for the telephone exchange where you want switching. Okay. And code converters. I will show you how can convert. I will take an example of code converters for this diode switching matrix, and that will be clear how it works. So another example is code converter. You can also have combinational shifters, adder, multiplier. But I will show only the code converter. We will convert BCD to decimal using the diode switching matrix. Okay. This BCD to decimal we also performed with encoder, isn't it? BCD to decimal or decimal to BCD. Okay. So now we'll see this BCD to decimal using the diode switching matrix. Yes, decimal to BCD it was. Now I have BCD to decimal. What is this? Code converter as a diode switching matrix. So for this, I will draw this switching matrix here. See, I have this 8, 4, not 4, 2 and 1. Okay. Let me give some time. I will draw it quickly. Okay, how to convert BCD to decimal? So you should have 4 bits, and each will have the weightage 4 to 1, and now 0 0 0 0, so 0 0 0 1 0 0 0. Actually, I am showing the process, otherwise you won't remember how to draw it. Okay, so this is 0 0 0 1 1 0 1 0 0. Four, 5, 6, 7, 8, and 9. So this will show your 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so now the weightage of this 8, if I connect to 1, so it will have 6 zeros in the row. It means this will be a 2, this will be a 3, 4, 5, 6, 7, 8, 9, and 10. This is last 10. So here I should connect it. Okay, now for this, okay, so for 0 0 0, I have connected in this way. Let me complete, then I will explain it. It will not be possible, I think, for these two and these two. Okay, now this is 0 and 1. So there will be a switch in this way, and this defines 1 and this defines 0. Here 1 0 and 1 and 0. Now again 2. Where is 1 1? This is for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, it was a problem. Actually, sorry for this. Actually, I should represent this using the PPT, because the circuitry is very complex. But no problem, now we have completed it. These are the diodes. Okay, and 2. So this will be now connected in this manner. Here these are the diodes. Okay, correct. Now I want to represent 6. So 6 means what? See there. What it will be? 0, 1, 1, 0. So this 8, this switch has the weightage of 8. Okay, and this switch has the weightage of 4, similar way 2 and 1. So here 8 will be 0. So here I will connect it to 0. This line is representing 1 and this one is representing 0. Again, this is 1 and 0, 1, 0, 1, 0. So 4 will be connected to 1, and again 2 will be connected to 1, and 0 will be connected to 0. Correct. Now, how it will work? See, this is my 5 volt and ground, it means 0. So what happened to this diode? This is 5 and there is no connection. So this line here, it will come, and again you see this is 5 volt and it is connected to 0 volt. So this diode will be in forward bias. Correct? So the whole voltage will drop across this. So this 0, there are LEDs connected to each lines. 0, 1, 2, 3, 4, 5 and 6. Okay. So here you don't have a 5 voltage. It means this LED will not glow. Again, we will move on and we'll see, will this work? No, because this is connected to 1. So it means the whole voltage, this will complete the path of this circuit. So again you have 0 volt here. For this also, and till this position, this 5 volt will come and this circuit will complete here. For this here, see, this is 4th line, and now I have a connection here with this 2. Correct? So again this path will be completed and the voltage will be dropped. Where we were at the 4th position. Now 5 again the similar, because this switch at the weightage of 2 is connected to 1 position. So again you have a voltage circuit, or you can say the voltage drop, and here the circuit will be completed. For this 6, this diode is open. Now you don't have any diode here. This diode is open. Correct? Now you see, this is also open and this is also open. It means the whole 5 volt of that battery will be reflected to this, and this LED will glow. Except this will all will not glow, because you will have 0 volt in this line. Similarly, you can check for any other BCD numbers. Is it clear? So how to draw it? I think now you got how to draw it, because you should first write this BCD, and for all 0, 0, 0s, I have put 8 diodes here for this position. 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, and 2 diodes for that 0th line. So here you have 2. Again, for this, the 4 diodes for this 4 are connected to switch at 1 position, and after this you have 4 diodes in row. So these are the 4 rows, 4 diodes, and again 2 diodes. So I did not connect that. Yes. No. They should be connected somewhere. Yes, here. in this manner. Okay, you can find in the internet, they will show you clear picture. Okay, so here we complete this lecture.